In this lesson, we're going to learn about something called a titration. A titration is a very useful laboratory technique that allows us to determine the concentration of an unknown substance. Well, the substance would be known, but the concentration of it would be unknown. So we could consider something like pool water needs to be held at a very specific pH. It's got to be low enough that it's not going to allow algae to grow, but not so low that it will cause damage to your skin. Things like industrial laundry or many chemical companies, a lot of cleaners need to be very careful about the exact pH of their products. In an industrial laundry, they need to make sure that the pH of all of the linen that they wash is coming out right around 6.5. Anything lower than 6 feels really itchy on the skin. Anything above 7 feels similarly. So they need to keep it right around a pH of 6.5 so that it's close to the pH of skin. And so they're able to do that by doing a titration to measure what is the actual pH of this water. And so we're going to learn how to perform a titration. We'll do this in the lab, but we also need to be able to do the calculations involved. So let's start with that. Let's say I have a solution of an unknown concentration. Let's say I know it's hydrochloric acid, but I don't know the concentration. The concentration is a mystery. But what could I easily measure? Well, I could easily measure the volume. So let's say I just take 15 milliliters of it. And then I put it in a little Florence flask like this. This little Florence flask, let's use a different color so you can actually see it. I put it in this little Florence flask right here. And I put in an indicator, an acid-base indicator. The indicator that we will use in the lab is called phenolphthalein. It is a very interesting word. But what phenolphthalein does is at pHs lower than, at a pH that is less than 7, it will be clear. But at a pH above 7, it will be bright pink. It will suddenly transition to a bright pink color. And so we're able to figure out when is our acid when has it been neutralized? Well, if we know that, based on what we've learned about neutralization reactions, I could just start neutralizing it, right? I could take some sodium hydroxide and I can use a known concentration. Let's say I've got 0.001 molar sodium hydroxide. And then I'm going to use this burette here. This is called a burette. I can fill it with sodium hydroxide, and I can measure, let's say I fill it to this point, and I can measure my initial volume. So initial volume, I'm going to let some pour in until my solution suddenly changes color to that bright pink, telling me that it has been fully neutralized, and that'll be my final volume. If I just take the difference in those, I get my change in volume, which is going to be how much sodium hydroxide actually had to be used to fully neutralize that hydrochloric acid. So that tells me the volume of sodium hydroxide used in that reaction. So let's say, for the sake of argument, that this one is, let's say it's 35 milliliters. So what's happening inside of this Florence flask is I have this reaction occurring. I've got HCl plus NaOH is making water and NaCl. So when I take this reaction, if I take it until this has reacted exactly, so that these two have fully reacted, then I'm just going to be left with the pH of water, which is 7. And so anything above that, the slightest amount above that, and I'm going to get a bright pink. So if I add 0.0001 milliliters more of NaOH, boom, pink. And so my volume measurement is actually going to be very accurate to tell me when this is neutralized. And so with that in mind, the thing that's going to be true here, since this is a 1-to-1 ratio, the number of moles of my hydrochloric acid will be equal to the number of moles of my sodium hydroxide. And so that's what we're looking for in a titration. We're looking for a point where we know that the moles here are equal, that these 2 moles are equal. And at that point, then I can say the concentration times the volume of my hydrochloric acid will be equal to the concentration times the volume of my sodium hydroxide. Why is that? Well, remember, our concentration is just equal to the number of moles divided by volume. And I can rearrange that to say that the concentration times the volume equals the number of moles. And since the number of moles here is equal to the number of moles here, it stands to reason that CV will equal CV. And so once I have that, I can take all of these numbers over here. I can take this unknown concentration, leave it in. My volume that is known, that 15 milliliters, it's going to be 0.015 liters, will be equal to the concentration here, that's 0.001, times the 35 milliliters, that's 0.035. Then I just rearrange this equation, and I'm going to get concentration equals 0.001 times 0.035 divided by 0.015. And I end up with a concentration 0.00, what was that? How many zeros? 2 zeros. 2, 3. Concentration of 0.0023. So I can bring that back up here. Now I know that concentration, 0.0023 molar. And I could even figure out the pH of that hydrochloric acid. It's going to be 2.64. So we should be able to calculate the results of a titration, because all we're doing is gathering 3 pieces of information. The volume of my unknown, which we set. We're the ones who put that in the Erlenmeyer flask. And then we have the concentration of the thing that is doing the titrating. That is unknown. We would know the concentration of that material. And then all we're doing is adding it until we know that it is evened out based on that phenolphthalein, and then we would know our volume. And then we just plug it in to this equation. So for any titration, that's really all we're looking for. We're just looking for the concentration of each one, the volume of each one. And we're able to get most of that information very easily. There's one other thing that we want to be able to do with the titration. We want to be able to graph these. This is going to be very important for future chemistry when we start to look at things like titrating a weak acid or a weak base. We want to be able to examine how that titration curve is affected. And so we're going to have pH as our y-axis, and the volume of our titrant added, which in this case was NaOH. And so what did we say our neutralized volume was here? Well, that neutralized volume was 35 milliliters. So we're going to set 35 milliliters as our middle point. Let's say that is 35 milliliters. And what was the initial pH of our solution? Let's just say this is going to be 7, this is going to be 14, and this will be, well, that'll be 0. So what was our initial pH? Well, our initial pH was 2.64. So we can say that before we add any of our NaOH, our pH, and that'll be about 3.5, so that'll be about right there. That'll be about our 2.6. So before we add any of our titrant, our pH is sitting at 2.6, right there. Let's do another color for this. Our pH is sitting right here. And then when do we get to a pH of 7? Well, we get there when we get to 35 milliliters. So we get there. Now, a titration curve has a very specific shape. And we could go through the calculations, the neutralization calculations, but if I just add 1 milliliter of NaOH, I'm hardly going to use up any of that HCl. We saw in our neutralization reactions that even if I used up half, even at my halfway point, which would be right here, my pH barely goes up. And so when we draw a titration curve, it's going to be a pretty straight line, and then all of a sudden it's going to jump up. It's going to be a very straight curve. So it's going to be moving very quickly up. And then if I were to keep adding sodium hydroxide, even just a little bit, even just a couple milliliters, it's going to send that pH skyrocketing. And so we get this curve for a titration. And now this is important to notice, that between these 2 points, I might go from a pH of 5 and jump to a pH of 10, and I might only change the volume of titrant added by maybe 3 milliliters. That might be as little as it takes to jump in that pH. And so when we talk about that midpoint, that 7 pH midpoint, where that phenolphthalein turns pink, it is going to be a very short distance for that to go. It is going to go, even if it turns pink here, even if it changes color there, the amount of volume that I measure is still going to be very accurate. It's going to be very close to that exact volume that it would take to fully neutralize that pH. And so because these titration curves take on this very distinctive shape, having this very distinctive curve where they skyrocket from a low pH to a high pH with just a few drops, because of that, it allows us to be very accurate, even with pretty inexpensive equipment like a Erlenmeyer flask and a burette.